Professor Alan Yu from JHU. This talk is also pre-recorded, so if you want to ask questions, you'll need to ask a question at the panel discussion. Professor Alan Yu is a Bloomberg Distinguished Professor at JHU with appointments at both Cognitive Science Department and Computer Science Department. Professor Alan Yu completed his PhD in theoretical physics at Cambridge University, supervised by Stephen Hawking. His computer vision research has been widely recognized and cited, winning several prominent prizes, including the Mar Prize and the Helmholtz Prize. So we will have Alan's talk pre-recorded.
Hello. So my talk is on out-of-distribution testing and generative models. So I'm motivated by trying to have AI algorithms that can work at the level of human intelligence or beyond. In other words, sort of strong AI. And, there's been a lot of progress over the last 10, 15 years using machine learning data-driven methods like deep networks. And so we get very big performance increases, particularly if we use standard performance measures. But despite all this, AI vision falls far short of human vision. Human vision is much more general purpose, much more robust. So, so how can we develop algorithms that are as good as humans? Now, I argue that, perhaps surprisingly, one of the problems facing AI is that our current train and test paradigm is somewhat misleading and can delay progress. So tougher tests, like using out-of-distribution testing, are one way to go forward. And I suggest that the generative models are a promising way forward, and I'll illustrate them by some examples on what we call compositional models. So first, what do humans perceive? And a human looking at these images will be able to not just classify the object as a helicopter, there's a boy. A human vision, a human observer will be able to estimate the 3D pose, the 3D structure of things, estimate the material properties of objects, etc., know if objects are clean, dirty, etc. We can also use that information to predict what's going to happen. If you look at the boy on the bottom right picture, you see his right foot is on a book. The book may slide, he may fall over. His right hand is close to a light bulb. He might touch the light bulb and burn himself and cry for his mother. So there's a lot of information that humans can get from these images, which is some way beyond what we can get with current AI algorithms. Now, the standard train test paradigm, what I mean is that the training and test data comes from the same underlying source. So this is some type of balanced annotated data set. And there is a nice theory which says that if you train algorithms and test them and the performance is high, then the good performance is likely to generalize to data that you haven't tested it on. So very nice mathematical theory, but doesn't really apply to vision, partially because the space of the images is much too big. These performance measures sort of, I think, ultimately historically go back to Bayes' risk, the idea that you evaluate the performance of an algorithm or decision process, alpha of x, x is the input, an image, for example, y is the output, classification, boy, light bulb, etc. You have a loss function for if your algorithm makes a mistake, and you try to evaluate performance by the Bayes risk, the expected loss. Okay, now in practice, you don't have those probability distributions. What you have is samples, and so you evaluate the algorithm by the expected, by the empirical risk averaged over the samples you have. So this is what we use in most AI, in evaluating most AI algorithms, particularly in vision. And it's got various assumptions, particularly that the training data comes from the same distribution as the test data. So, this is attractive. It's what we've used for the last, 15, 20 years. But there are certain problems with it. As we know with deep nets, if you do small changes to the images, these can make very big changes to the output of your algorithms. So here is an example that we had from CVPR 2022. This is a visual questioning answering algorithm. The question is, what is the color of the dress of the woman's, the woman tennis player? The answer is clearly orange. And that's the answer that the algorithm gives you if the ball that the woman is hitting is really a tennis ball. However, if you modify the image slightly by replacing the tennis ball with a football, as in the right-hand side, then the algorithm decides that the color of the dress is white. Why? Well, this is a deep network, so we have no idea why a small change like that can make the network think that the dress is white. But the point here, small changes like this can make the algorithms have catastrophic errors. This is obviously only one of many examples. There's a lot of work demonstrating this type of thing. So suggests a problem with how we're currently evaluating algorithms because, they shouldn't make these types of mistakes. A general point is that the train test paradigm favors regression type models. The optimal strategy is to learn P of Y given X. X is the output. Y is the output, X is the input. Deep networks learn approximations to these. I should mention here, when I say regression, I mean it in the statistics sense, which means it can be discrete or it can be continuous, makes no difference. But in any case, if you're in this situation with balanced data sets, the train test paradigm, the best thing you can do basically is learn a good regression model. Okay, so it gives those methods an unfair home field advantage compared to alternatives. This also means that these algorithms, particularly deep nets, are wonderful at overfitting the data sets, which is good for getting papers published, but may risk failing to generalize to data that comes from other distributions or data in the real world. Okay, so out of distribution testing helps address this by having models that have deeper understanding of the data. And various researchers outside vision, like Bernard Scholkopf, have argued for out of distribution testing for the perspective of doing causal learning. And Newton's theory of gravity is a nice example. Before Newton, you had the Ptolemaic theory of the solar system, which gave very good predictions of the motion of the planets. It was based on 40 assumptions that the planets moved around the sun, etc. But they'd had a lot of data. They tweaked the model to fit all the data. It was data-driven, and it gave very good predictions. And Newton's theory, however, was causal. It didn't just explain how planets move, but it also explained why apples fall to the ground and many other phenomena. So it's a deeper theory, a far better one than the Ptolemaic theory. Now, there is already, I realized 20 years ago, in fact, the first work I ever did on data sets, we actually had a theory we actually did an out of distribution type task for edge detection. And the reason for that was that there were two data sets with edges annotated in them, and they were really quite different. Now, we were not using a regression model on the data sets we did not train for the probability of the output y given x. This is what standard deep networks do for edge detection. Instead, we learned a generative model, probability of feature response given y, given whether it's an edge, y equals 1, or no edge, y equals 0. And the advantage of this was that we learned that we sort of separated out the prior p of y and the generative model p of x given y, was that we were able to generalize from one data set to the second and back from the second back to the first. So an early proof of generative models, details for this, the paper is still available online, so you can check it out if you're interested. Now, out of distribution testing, and there are examples of this work, and I'll discuss them in a little bit more detail later on when I talk about compositional models, but they include work where you have occluders. So you train the algorithm on data where there are no occluders, but you test it when there is occluders. So that's out of distribution. The test data is noticeably different from the training data. And in those cases, the regression-based deep network methods performance starts failing as the amount of occlusion rises, but generative models still perform fairly well as you have more occlusion. Also, in other work, a data set that's going to be in ECCV 2022, so at this conference, you have examples of images, cars, motorcycles, etc. Then you can change the pose, you can change the texture, you can change the context, you can change the weather, and you can try to generalize algorithms trained on the normal data to see if they work under these types of conditions. And models that do this, I'm sure, a number of approaches to do this are still, in a sense, regression-based approaches with certain sort of tweaks or modifications to it. But as I'll describe, you can deal with all of these with generative models. Now, in addition to, this case of wanting to have out of distribution data, so to test your algorithms with average case performance on data that's somehow different from the data you trained it on, you can also argue that average case is problematic. Sometimes maybe you want worst case if you don't want to fail to detect a baby in the road. More generally, however, data sets are biased. That's, most people would know that and admit it. So average case is with respect to an average, respect to a biased data set, which means that average case perhaps is not the right measure to use. ImageNet is biased to contexts. Certain work we did, illustrated that. Other cases on other edge detection work, you could show that performance on data sets, while appearing to improve performance, was really fitting the biases in the data set. We did that, I think, about 9 years ago. Xiaoli Ho, now CEO of Too Simple, did it. And I guess this paper wasn't a big hit at the time, but it's still being cited. So there was a point there. You can start overfitting the data, overfitting the data set, and that's not good. Now, more radically, the idea was you should try adversarial examiners. We've had a series of papers on these, which try to say that when you test an algorithm, you don't just test it on random samples for anything. You set the situation up so that you can have an exponentially number of possible stimuli that you can show to the algorithm, and then at test time, you search through this set of stimuli to find the ones that can find error measures in the algorithm. Random sampling, we take it for granted perhaps in machine learning, but think about it. If you want to test your students or your professors, you wouldn't do it by asking them a random set of questions. You'd ask them a series of questions where the answer to one question depended on the question you asked will depend on the answers to previous questions. And adversarial examiners give a way to test algorithms in that sense. So an example here, adversarial patch attack, means that you can take images, you can put in patches that you learn from a dictionary, you can select them from a large possible dictionary, you can move them around, you could change them. And so you have a huge combinatorially big set of stimuli that you could use for the algorithm, that you could test the algorithm on. You learn a control policy for deciding which images to test the algorithm on based on its response to earlier images. And you can attack deep networks incredibly successfully, targeted black box attacks without knowing anything about the interior of the algorithms. Here's another recent example from CVPR 2022 from Nathaniel Ruiz, Boston University, in a collaborative project. And here, this is for face recognition, use a synthetic system to generate stimuli, and you follow the same adversarial examiner approach. You can modify the stimuli at test time by seeing how well the deep nets respond, or whatever you're testing it on, respond to your stimuli. And so over here on the right-hand side, the green lines show the performance if you just do random sampling. And so basically, if you do random sampling, you don't find any problems with the algorithms. If, however, you do adversarial examiners, you're searching for the worst stimuli, then the performance goes down with these orange lines, because initially you're sort of exploring the space a little bit randomly until the algorithm starts finding weaknesses of the algorithm, in which case it, explores those weak places of the algorithm and finds its failure modes. So these are additional ways of testing algorithms. So I think they're far better than the standard approaches that we're using. So out of distribution, out of task, meaning that you train the algorithm to do one task and then test it on another. Domain transfer, which depending on your views can be called out of distribution, etc. You can use those types of tests, evaluation, and you can also test robustness to adversarial examiners. So now I will describe briefly a set of generative models that can be proof of concept that it's possible. I gave a talk a bit like this, a virtual talk to Stanford during the pandemic, and the student asked me politely afterwards, well, okay, if you do all these types of tests, maybe no algorithm is going to survive them, and maybe you're trying to make things too difficult. And my response is, yeah, that's possibly true. So that's the challenge that we ought to try and address. So here is some work that's done with a range of people, particularly Adam Kortulewski, who's obviously main organizer of this meeting, and with a host of students who made some very nice contributions to it. So what we have are what we're calling two-dimensional compositional networks, and these give generative models of deep network features. The next slide will illustrate that a little bit more carefully, and in these models, an object is represented by a mixture of different generative models. The mixtures would roughly correspond to different viewpoints. They don't exactly if you try and quantify it, partly because the algorithms are learned without supervision, they're learned in an unsupervised way, etc. And the feature vectors are represented by a dictionary of visual concepts. So the model has certain latent variables in it, which is a distinction between it and standard deep networks, and also is generative. Inference on this model is done by feed-forward processing, somewhat similar to a deep network. The computations are not so difficult. The learning of these models is more complicated because you've got to learn this internal structure. Okay, so the models, however, are generative, so they are specifying probabilities for generating the data if an object is present and if a particular viewpoint occurs. Now, it's possible to modify them to include an outlier process. So this means giving the generative model the knowledge that part of the data might have been generated by something other than the object that is in the, that's in the image. It could be generated by a car. Most of it will be generated by a car, but some will be generated by something else. So this introduces another latent variable, which allows the algorithm to decide, is part of the data, is it generated by the car or by this outlier occlusion process? Similarly, you can introduce a simple background model, again, learned without supervision, which can generate the background, leaving the 2D compositional networks to generate the foreground, also activated by latent variable. So there's certain knowledge about the world that can be expressed nicely in generative models, which is harder to see how it could be used in discriminative models like standard deep networks. So what do? The work is basically, it's mainly on vehicles. There are issues, complications with the 2D comp nets. They don't scale as nicely as deep networks. And we concentrated the work on vehicles, although it was scaled up to 50 and I think possibly 100 objects as well. But the main points is that they perform comparably to deep networks if you use standard measures, the standard train and test paradigm. But if you do out of distribution, if you test them on data with significant occlusion, they perform better. Essentially, they've got a model within them that helps decide if the data is generated by the object or generated by an occluder. Then, with the patch attacks I mentioned earlier, the adversarial examiners where you put patches into the image, the 2D comp nets are orders of magnitude more robust, much more robust than the deep networks. Now, the 2D comp nets can detect the boundaries of multiple overlapping objects, cars, that's a CVPR 2001 paper, and they can also detect objects and estimate modal boundaries better than deep nets. Modal boundaries are the boundaries of the object, which are which you cannot see because they are occluded. And finally, they can also do domain transfer. So for these, there are a series of papers that the citation for people who are interested, but these models have the capability of dealing with these out of distribution challenges, the adversarial examiner performing different tasks from the ones they were trained on, with a sort of a uniform underlying theory, and they can do it essentially because they are generative. So here is the idea. So a standard deep net has all these nice feature vectors, and then you train a model for the output, y being classification. You learn P of y given f, where f are all the feature vectors. The 2D compositional networks keeps the backbone, keeps the features, and then trains the model to learn P of f given y. This becomes a generative model, so you're switching the last stage here from going forward to going backwards. This enables you to use a lot of the advantages of generative models. So here for the outlier process, we've got the generative process for the object, but then we have an additional process that can be switched on and could generate occluders. This means that the algorithm, while it's looking at an image and trying to interpret it, has to keep deciding locally whether something is part of the object or is an occluder. Computation is a little bit more complex in a deep network, but not significantly so. And so adding an outlier process makes the algorithm more robust to occluders, and also it can locate them because the latent variable Z to decide if the data is generated by an occluder will switch on if it thinks there's an occluder. The same process also makes this compositional network robust to adversarial patch attacks because it will observe there's a patch that's inconsistent with the rest of the image, and it will switch it off by saying that it's an occluder. So here are some studies. Here are deep nets. They don't work, they don't generalize well. I mean, they don't do badly, but they, performance drops by 36% as you increase the amount of occlusion from 0 to 70%. If you do it with compositional networks, performance is dropping, but it drops far more slowly. It drops down to, here you're dropping down 20%. That's a lot better than dropping down 36%. There's quite a lot of work on this. We have a conference paper, we have a journal paper, and it was also done for object detection as well. So a lot of robustness without needing to be trained on the occluded data at all. Adversarial patch attacks, the same mechanism, as I said, work fairly well, and here are examples. Here is the attack success rate of the patch attacks on a BGG16. You get similar results for attack on a ResNet, and they're very, very high. Here is the success rate on the CompNets. The success rate of the attack is now down to 10%. Here is SparseRS is another, it's a slightly later version, I think, from Germany, which is nicer than patch attacks in some way, and you get the same story. The CompNets, in this case, are robust by a factor of 100 compared to the deep nets. Okay, ability to detect boundaries, and so this is out of task testing. You're training the algorithm only to classify the object, but because it's got within it these latent variables, it can also do a modal completion, estimating the boundaries which are not visible because they're occluded, and multi-object reasoning, as shown here. Domain transfer, this is more recent. I guess this is actually in submission. The deep net, the algorithm is trained to adapt from one domain to another. The ability here to use generative models is that the compositional model is generating feature vectors which are represented by clusters that we call visual concepts and which correspond roughly to parts of objects. I say roughly because if you try and quantify them, they're not great, admittedly. Nothing is, but so visually, conceptually, they're somewhat similar to parts. And these can be learned in data sets without having any annotations. You learn the dictionary of these basic part-like elements, and that enables you to train an algorithm on one data set where you have the annotations and transfer it over to another. And so that work is performance is pretty good on all these tasks on this data set we had, where the context changes, the weather changes, the viewpoint, the texture, and the pose changes. So again, you could argue that this is an advantage of the generative approaches. So the 2D CompNets give proof of concept that algorithms can perform well on these tougher performance measures. They can deal with out of distribution, they can deal with out of task, and they can deal with some adversarial examiners. And they do this by being generative, using the advantage of deep network features, but they have more structured representations of objects and latent variables in them. But certainly, I don't want to suggest that 2D CompNets are the solution to vision at all. But they're only a starting point for us. But in any case, they do show that it's possible to have algorithms that can perform well as state-of-the-art methods if you use the standard performance measures, but which are able to do out of distribution as well, a lot better than the standard methods, and can do domain transfer out of task testing. So, conclusion, going back to the beginning, I think we're in a train test paradigm, which, if we use balanced annotated data sets, is favoring regression-based models. We've got good performance on those. That's actually taken computer vision a long way. And I certainly remember when, for example, deep nets came in, you made changes to them, you modified them, you applied them to a task, you got huge improvements in performance. But those days are gone. We don't get huge improvements in performance anymore with these methods. And so I think we need to consider stronger tests, stronger challenges for the algorithms. And we need to develop algorithms that have the ability to withstand these stronger tests, and the conversational networks are examples of them. They're not, they're not the final solution to these types of problems at all, but I think the idea of them being generative is pointing in a direction to get algorithms that may be able to ultimately produce systems which have strong AI and perform as well as humans and potentially better than humans. So, but I'll leave you with the thought that if we want AI algorithms that perform better than humans, then we will need to test them strongly. And if we only test AI algorithms weakly, we will only get weak AI. So that's why out of distribution testing is very important. And adversarial examiners are even more important. And from my perspective, generative models are a very promising way to deal with these challenges. Okay, well, thank you very much. I've gone a minute or so over time, so sorry about that. And goodbye for now.